Imagine staring up at the night sky, thinking you know the universe only to discover its hiding secrets so strange they defy everything you thought was possible. Out there, beyond the familiar twinkle of stars, lies a cosmos teeming with riddles that even scientists struggle to explain. From rogue planets drifting through the void without a sun to black holes that sing in eerie, cosmic frequencies, the universe is weirder than any science fiction. And today, we're diving deep into 30 of its most mind-bending oddities phenomena you've likely never heard of, each one more baffling than the last. Picture this: a star so dense, a single teaspoon of it would weigh as much as a mountain, or a galaxy made almost entirely of dark matter, invisible to our telescopes yet bending the fabric of space itself. These aren't just curiosities, they're clues to the universe's greatest mysteries, pieces of a puzzle we're only beginning to assemble. Every discovery rewrites the rules, challenging what we know about reality. And that's what makes space exploration so thrilling. It's not just about finding answers, it's about stumbling upon questions we never even thought to ask. This journey isn't just for astronomers or physicists, it's for anyone who's ever looked up and wondered what else is out there. Whether you're a casual stargazer or a seasoned science enthusiast, these cosmic oddities will leave you in awe. Some will make you question the laws of physics, others might send a chill down your spine, but one thing's certain: by the end, you'll see the universe in a whole new light. So let's begin, because the cosmos has been waiting to show you its strangest secrets. Among the countless celestial oddities lurking in the cosmos, few are as eerily poetic as the Black Widow Pulsar. Imagine a neutron star, a corpse of a once mighty sun, now crushed into a sphere no bigger than a city yet spinning hundreds of times per second, whipping beams of radiation across space like a cosmic lighthouse. But this particular pulsar isn't just spinning, it's feeding. Like its namesake spider, it's slowly consuming its stellar companion, a hapless star locked in a deadly gravitational embrace. Discovered in the late 1980s, the Black Widow Pulsar stunned astronomers with its violent behavior. It doesn't just orbit its partner, it bombards it with relentless gamma rays and charged particles, stripping away layers of gas and dust in a process called ablation. Over millennia, this relentless assault will eventually leave nothing but a ghostly remnant. What makes this system even weirder: the pulsar's gravity is so intense, it distorts its companion into a teardrop shape, stretching the star like cosmic taffy. But the Black Widow's deadliest weapon is its radiation. Those gamma-ray jets, they're among the most energetic phenomena in the universe. If you were foolish enough to venture near this system, though you'd never survive the trip, the sheer force of those rays would rip apart your atoms. And yet, despite its brutality, this pulsar is a goldmine for scientists. It's a natural laboratory for studying extreme gravity, particle acceleration, and the fate of binary stars. Plus, its eerie nickname isn't just for show. Just as a Black Widow spider outlives its mate, this pulsar will one day stand alone in the darkness, the last survivor of a cosmic tragedy. Just when you think space can't get any stranger, along comes a cosmic structure so precise it looks like it was drafted by the universe's own architect, the Red Rectangle Nebula. Floating about 2,300 light-years away in the constellation Monoceros, this isn't your typical swirling cloud of gas. Instead, it's a near-perfect geometric wonder, its crimson hues framed by intersecting beams of dust that form an almost rectangular shape. Scientists believe this eerie symmetry comes from two cone-like jets of material, ejected in opposite directions by a dying star at its heart, a star that's essentially painting the cosmos with its final breaths. What makes this nebula truly bizarre isn't just its shape, it's the chemistry behind that deep red glow. Unlike most nebulae, which shine from the ionization of gases like hydrogen or oxygen, the red rectangle's color comes from something far more exotic: complex organic molecules known as polycyclic aromatic hydrocarbons. These sprawling, carbon-rich compounds are typically found in soot or engine exhaust on Earth, but here, they're woven into the fabric of space itself, lit up by the intense ultraviolet light of the central star. It's like finding a cosmic fingerprint of chemistry we associate with pollution only in this case. It's sculpting one of the most beautiful structures in the galaxy. Compared to the chaotic splendor of the Crab Nebula or the delicate petals of the Rose Nebula, the Red Rectangle feels almost artificial in its precision. But that's the real magic of it. Nature doesn't need a ruler to create geometry this flawless. Over thousands of years, the dying star's steady, rhythmic pulses of gas and dust have carved this masterpiece, a testament to the invisible forces shaping our universe. And here's the kicker, we're witnessing it at just the right moment. In a few thousand more years, the star will shed its outer layers entirely, leaving behind a glowing core that will illuminate the nebula even brighter. By then, the Red Rectangle might transform into something else entirely, a fleeting cosmic artwork, visible only for a blink in astronomical time. Among the countless galaxies swirling through the universe, Hoag's object stands out like a cosmic bullseye, a near-perfect ring of blue stars encircling a golden core, floating in the void with no visible connection between them. Discovered in 1850 by astronomer Arthur Hoag, this peculiar galaxy defies everything we know about how galaxies form and evolve. It's not a spiral with winding arms, nor an elliptical blob of ancient stars. Instead, it's a pristine ring, so symmetrical it looks like it was drawn with celestial compass. What makes Hoag's object so baffling is the sheer isolation of its components. Most ring galaxies form after a smaller galaxy plunges through the center of a larger one, sending shockwaves through the stars and gas that ripple outward in a ring. But here's the catch, Hoag's object has no visible collision partner, no remnant of a galactic trespasser that could explain this perfect structure. Even more perplexing, the gap between its glowing core and the outer ring is eerily empty, as if someone carved out a slice of space and left only the edges intact. Peering deeper only deepens the mystery. The central core is packed with old, reddish stars, typical of ancient galactic cores, but the outer ring, that's a stellar nursery, brimming with young, hot blue stars and glowing pink clouds of ionized hydrogen, evidence of furious star formation. This stark contrast suggests two entirely different eras of stellar life coexisting in one object, separated by a vast, starless moat. Some theorists propose that Hoag's object might be the aftermath of a long-ago collision we can no longer see, while others wonder if it's the result of gravitational instabilities we don't yet understand. And if one cosmic riddle wasn't enough, take a closer look at the background of images capturing Hoag's object. Lurking even farther away is another, fainter ring galaxy, a possible twin that raises even wilder questions. Could there be a yet undiscovered process that creates these celestial donuts? For now, Hoag's object remains a beautiful enigma, a reminder that the universe delights in breaking its own rules. Every time we think we've figured out how galaxies work, something like this comes along and turns the textbook upside down. There's an invisible force in the cosmos so powerful, it's dragging entire galaxies toward it like a cosmic magnet, and we can't even see what's doing the pulling. This is the Great Attractor, a gravitational mystery lurking behind the Milky Way's crowded star fields, where dust and gas shroud our view like a cosmic curtain. For decades, astronomers have known something strange is happening in this direction. Thousands of galaxies, including our own, are streaming toward it at speeds of over 600 miles per second. But what's causing this colossal tug of war? The answer is buried in one of the universe's most frustrating blind spots. The Milky Way's disk creates what scientists call the zone of avoidance, a region where our galaxy's own stars, gas, and dust block our view of the universe beyond. It's like trying to peer through a sandstorm. The Great Attractor sits right behind this veil, making it nearly impossible to study with traditional optical telescopes. But here's the twist: we've learned to see it anyway. By mapping the motions of galaxies with radio and infrared telescopes, astronomers have pieced together a shadowy portrait of this gravitational giant. What they found is a staggering concentration of mass, roughly equivalent to tens of thousands of Milky Ways clustered together, yet the plot thickens. The Great Attractor might not even be the main culprit. Recent observations suggest an even larger structure lurking beyond it, the Shapley supercluster, a gargantuan assembly of galaxies exerting its own gravitational pull. This cosmic tug-of-war between unseen forces raises a tantalizing question: are we being drawn toward one colossal attractor, or is the universe's large-scale structure far more complex than we imagined? The answer could rewrite our understanding of how matter is distributed across the cosmos. What makes this mystery so thrilling is its scale. The Great Attractor isn't just pulling a few nearby galaxies, it's influencing a volume of space hundreds of millions of light-years across. And the real kicker: we're caught in the flow. Our local group of galaxies, including Andromeda and the Milky Way, is riding this cosmic current, destined to merge with the attractor's heart in billions of years. It's a humbling reminder that even as we map the universe, we're still passengers on its grandest currents, pulled by forces we've only begun to comprehend. In the asteroid belt between Mars and Jupiter, where rocky leftovers from the solar system's formation orbit in predictable silence, one object refuses to follow the rules. Meet El Pizarro, the cosmic rebel that blurs the line between asteroid and comet, a celestial chimera with the body of a rock and the soul of a snowball. Discovered in 1979 and originally catalogued as asteroid 1979 OW7, this oddity stunned astronomers in 1996 when it suddenly sprouted a glowing tail like a comet, despite orbiting in a region where ice shouldn't survive. What makes El Pizarro so extraordinary is its dual nature. Most asteroids are dry, rocky fragments, while comets are icy wanderers that grow luminous tails when sunlight vaporizes their frozen gases. But this object defies categorization. Spectroscopic analysis reveals a surface of dark, carbon-rich rock typical of asteroids, yet somehow, it periodically erupts with jets of dust and gas, forming a tail that stretches hundreds of thousands of miles. The leading theory: hidden reservoirs of subsurface ice, protected by a rocky crust, occasionally get exposed by cracks or impacts, creating sporadic outbursts. It's as if someone buried a comet inside an asteroid and forgot to tell the universe it wasn't supposed to happen. The debate over how such hybrids form splits scientists into two camps. One group argues these are main belt comets, true asteroids that somehow retained primordial ice from the solar system's birth, 4.5 billion years ago. Others propose they're the shattered remains of larger, icier bodies, their frozen interiors exposed by ancient collisions. But here's the twist: El Pizarro's activity doesn't follow the predictable, sun-driven cycles of normal comets. Its outbursts seem random, suggesting hidden mechanisms like buried pockets of volatile gases or even seismic shifts cracking its surface open like an egg. What's at stake isn't just a label. If objects like El Pizarro are common, they could rewrite our understanding of the asteroid belt's history. Water, essential for life, might be locked beneath the rocky surfaces of countless asteroids, preserved far closer to the Sun than we ever imagined. Future missions could target these hybrid worlds, mining their ice for deep space exploration, or even uncovering clues about how water arrived on Earth. For now, El Pizarro remains a tantalizing puzzle, a reminder that even in the crowded asteroid belt, nature still has surprises up its sleeve. Somewhere in the constellation Boötes lies a cosmic nightmare, a void so vast and empty, it defies comprehension. Stretching 330 million light-years across, the Boötes void is a staggering bubble of near-nothingness, a region where galaxies should be packed like fireflies, but instead exist as rare, lonely specks. Astronomers call it the Great Nothing, and for good reason. If you place the Milky Way at its center, our nearest galactic neighbor would be so far away, its light would take millions of years to reach us. It's the universe's most unsettling silent zone, a blank canvas in a cosmos obsessed with filling every inch of space. So how does a void this massive even exist? One theory points to the universe's early foam-like structure, where quantum fluctuations left some regions stretched thin, while others clumped into galaxy clusters. Over billions of years, those underdense areas expanded into colossal bubbles, cosmic Swiss cheese holes where gravity lost the tug of war. But here's the twist: the Boötes void is too big. Simulations struggle to explain its scale without invoking exotic physics or unseen forces. Some researchers speculate it could be the imprint of an ancient collision between parallel universes in the multiverse, a scar left behind when realities brushed against each other. Then there's the wildcard theory. What if it's not empty at all? Dark energy, the mysterious force accelerating the universe's expansion, might concentrate in these voids, pushing matter away like an invisible repellent. Or cue the chills, could it be evidence of a Type 3 civilization's unfathomable engineering? The controversial Dyson swarm hypothesis suggests advanced beings might harvest entire galaxies for energy, leaving behind hollowed-out shells. While there's no proof, the sheer scale of the void makes even fringe ideas hard to dismiss outright. Yet the eeriest part isn't the theories, it's the silence. Surveys have found fewer than 60 galaxies in the void, a number so low, statisticians call it cosmologically impossible. Those that do exist are often oddballs, isolated, blue, and strangely youthful, as if the void preserved them in time. One named MCG+002 drifts alone with a warped disk, its spiral arms twisted by the nothingness around it. It's a ghost ship adrift in the universe's emptiest ocean. Staring into the Boötes void forces a humbling realization. We think of space as crowded and vibrant, but this gaping hole reveals how much of the cosmos might just be absence, and perhaps that's the most unsettling truth of all. Some corners of reality weren't built for life, light, or even matter. They're just endless, indifferent dark. Of all the stars in our galaxy, few have stirred as much intrigue or wild speculation as Tabby's star, officially known as KZ 8462-852. Nestled in the constellation Cygnus, this seemingly ordinary F-type star became infamous in 2015 when astronomers noticed its light was doing something impossible, dimming erratically, sometimes by up to 22%, in ways no natural phenomenon could easily explain. Most stars experience predictable, gentle dips when planets pass in front of them, but Tabby's star flickered like a candle in the wind, plunging into darkness at irregular intervals before brightening again. The patterns defied logic, sparking a frenzy of theories, including the electrifying possibility that we were glimpsing an alien megastructure. The most sensational hypothesis suggested a Dyson swarm, a vast array of energy-collecting panels built by an advanced civilization, encircling the star and blocking its light in uneven chunks. It was a tantalizing idea, but science demanded colder, harder answers. Years of follow-up observations have since peeled back layers of the mystery, though none entirely solve it. One leading theory points to colossal clouds of dust, possibly from the breakup of a moon or planet, drifting in chaotic orbits around the star. Unlike solid megastructures, dust could explain why the dimming varies across different wavelengths. Light scatters more through fine particles than through massive objects. Yet even this explanation has holes. The dust would need replenishing constantly to account for the star's long-term fading, which has been recorded over a century of historical data. Some researchers propose a battered family of comets, shattered by a close encounter with the star, could be the culprits. Others wonder if Tabby's star is simply swallowing its own planets, leaving behind debris fields that intermittently block its light. Then there's the star's bizarre long-term behavior. While most variable stars brighten and dim in cycles, Tabby's star has shown an overall decline in brightness by as much as 14% over a century. No known stellar process accounts for this, leaving astronomers scratching their heads. Could it be aging unusually? Is some internal dynamic altering its output? Or is there still some unseen, dusty companion orchestrating this cosmic light show? What makes Tabby's star so compelling isn't just the unsolved puzzle, it's the lesson it teaches about discovery. Sometimes the universe throws us a curveball so strange, it forces us to question not just the answers, but the questions themselves, whether the culprit is dust, debris, or something beyond our current understanding. This star remains a beacon of cosmic humility, reminding us that the galaxy still has secrets we're not yet equipped to unravel. Deep in the constellation Serpens, a dead star spins at dizzying speeds, its gravitational pull warping spacetime like a cosmic whirlpool, and tethered to it, a world unlike any other. Meet PSR J1719-1438b, a planet so dense and bizarre, scientists believe it's literally made of crystallized carbon, a diamond the size of a world. Orbiting a millisecond pulsar 2,800 light-years away, this exotic gemstone challenges everything we thought possible about planetary formation. The story of this diamond planet begins with stellar violence. Its host, Pulsar J1719-1438, was once a massive star that erupted in a supernova, collapsing into a neutron star no larger than a city yet weighing more than our Sun. The explosion likely stripped away the outer layers of any nearby planets, but not this one. Somehow this surviving world, roughly 5 times Earth's mass, endured the cataclysm. What's left is a core so compressed, carbon atoms have been crushed into a crystalline lattice, forming what could be the largest diamond in the galaxy. Calculations based on the planet's orbit and the pulsar's gravitational influence suggest its density far exceeds normal rocky worlds. If you could stand on its surface, an impossible feat given its scorching temperatures and crushing gravity, the ground beneath your feet might glitter with continents of solid diamond, layered over a sea of even denser carbon phases like lonstellate, a rare form tougher than earthly diamonds. Yet the real mystery isn't just its composition, but how it got there. One theory posits it was once the carbon-rich core of a gas giant, its outer hydrogen and helium layers blasted away by the pulsar's radiation. Another suggests it's the corpse of a white dwarf star, stripped down to its diamond heart by the pulsar's relentless pull. Studying this world is a feat of astronomical ingenuity. Pulsars act as cosmic lighthouses, their beams of radiation sweeping through space with metronomic precision. By measuring tiny variations in the pulsar's spin caused by the planet's gravity, a technique called pulsar timing, scientists can infer details about the planet's mass and orbit. But the diamond planet itself remains shrouded in mystery. Its surface temperature, likely heated by the pulsar's intense radiation, could exceed thousands of degrees, turning what might be a glittering carbon landscape into a hellish pressure cooker. What makes this discovery so provocative isn't just the spectacle of a diamond world, it's proof that planets can form and survive in the most hostile environments, imaginable places where stars explode and gravitational forces twist the rules of physics. If worlds like this exist, what other impossible marvels might lurk in the pulsar's shadow? The universe, it seems, has a flair for turning destruction into something dazzling. Most galaxies age gracefully, birthing new stars and evolving over billions of years, but not in GC 1277. This cosmic fossil, lurking 220 million light-years away in Perseus, is the universe's equivalent of a living museum. Unlike the Milky Way, which churns out fresh stars like clockwork, this ancient behemoth froze in time roughly 10 billion years ago, becoming what astronomers call a relic galaxy, a snapshot of the early universe preserved in celestial amber. What makes NUC 1277 so extraordinary is what's missing. Its core is packed with old reddish stars, but the spark of new star formation is utterly absent. No glowing pink nebulas, no clusters of brilliant blue newborns, just a silent sea of ancient suns, unchanged since the universe was a quarter of its current age. Scientists believe this galaxy gorged itself during the cosmos's wild youth, devouring gas and smaller galaxies with such ferocity that it burned through its star-making fuel too quickly. Then, trapped in a sparse region of space with nothing left to consume, it entered a twilight state, becoming a stellar graveyard where time stands still. But here's the twist: relic galaxies like this shouldn't exist in today's universe. Models predict they'd either merge with neighbors or gradually rejuvenate by absorbing fresh gas. NGC 1277 defies both fates. Its isolation, perched like a lone sentinel at the edge of a galaxy cluster, may hold the key. Without nearby galaxies to disrupt it or new material to spark star birth, it's remained pristine, like a fly trapped in cosmic sap. Peering into its core reveals even greater mysteries. The galaxy harbors a supermassive black hole so disproportionately massive, 17 billion times the Sun's mass, that it challenges theories of how black holes and galaxies co-evolve. Normally, black holes grow alongside their host galaxies, but this one seems to have ballooned while the galaxy itself stagnated. Was this black hole unusually greedy, or did its growth somehow halt the galaxy's evolution? The answers could rewrite our understanding of galactic life cycles. Studying NGC 1277 is like unearthing a dinosaur bone still clad in flesh. It offers a rare glimpse into the era when galaxies were assembling their first stars, a time when the universe looked radically different. Every flicker of light from its aging stars carries whispers from the cosmic dawn, and decoding those signals might reveal why some galaxies thrive while others, like this celestial relic, simply stop. In a universe that never stops changing, NGC 1277 is a defiant monument to the past, challenging us to rethink how galaxies live, die, and sometimes refuse to do either. Some signals from the cosmos arrive like cryptic postcards, brief, intense, and utterly baffling. Fast radio bursts, or FRBs, are among the most enigmatic, flashes of radio waves lasting just milliseconds, yet packing as much energy as the sun emits in 3 days. Since their discovery in 2007, these fleeting cosmic sparks have puzzled astronomers. They erupt from distant galaxies, billions of light years away, with no obvious cause. Some blast once and vanish. Others, like the infamous FRB 121102, repeat in unpredictable patterns, as if the universe is teasing us with a code we can't crack. What makes these bursts so confounding is their sheer power paired with their brevity. Imagine a microwave oven, running for a fraction of a second, but scaled up to galactic proportions. The energy required is mind-bending, hinting at extreme astrophysical processes. Leading theories point to magnetars, highly magnetized neutron stars whose crusts can fracture under intense stress, releasing colossal bursts of radiation. Others suggest collapsing black holes or cosmic strings, hypothetical defects in spacetime itself. And yes, for a brief, thrilling moment, some dared to speculate about alien megastructures, though most scientists now consider natural origins far more likely. Then there's FRB 121102, the first repeater ever discovered, nestled in a dwarf galaxy 3 billion light-years away. This burst doesn't just recur, it cycles through active and quiet periods, like a celestial lighthouse with a faulty switch. Even stranger, its bursts are polarized, meaning their radio waves vibrate in a twisted pattern, as if they've traveled through a powerful magnetic field. This clue suggests the bursts might originate near a black hole or within a nebula dense with plasma, environments so extreme they warp the very fabric of space. Yet the biggest mystery isn't just where FRBs come from, it's how many there are. Current estimates suggest thousands might erupt across the sky every day, most going unnoticed. New telescopes like the Canadian Hydrogen Intensity Mapping Experiment are now catching them by the dozens, revealing subtle differences that deepen the puzzle. Some bursts exhibit scattering, where their signals smear slightly, hinting at turbulent material along their path. Others arrive with lower frequencies delayed by fractions of a second, a fingerprint of their journey through intergalactic space. What's at stake goes beyond curiosity. FRBs could be cosmic yardsticks, helping map the universe's invisible matter. As their waves traverse galaxies, they interact with electrons, leaving imprints that reveal the universe's hidden structure. Some researchers even propose using them to test Einstein's theory of relativity with unprecedented precision. But first, we need to understand what's creating these bursts and why some, like FRB 121102, insist on repeating. For now, they remain one of space's most compelling riddles, brief whispers from the depths of the cosmos, daring us to listen closer. GJ1214b isn't just another exoplanet, it's a cosmic paradox wrapped in a thick, steamy haze. Discovered in 2009, this so-called water world orbits a dim red dwarf star 40 light-years away, and from the moment scientists measured its density, they knew something was off. Here's a planet roughly 2.5 times Earth's size, yet nearly 7 times as massive, with a composition that defies textbook categories. If you could weigh it in some celestial scale, its density would land somewhere between a rocky world and a gas giant, hinting at a structure unlike anything in our solar system. The real shocker came when astronomers pointed the Hubble Space Telescope toward this alien world. Instead of a clear atmosphere like Jupiter's or a hazy one like Venus's, GJ1214b showed signs of something far stranger, a thick, global shroud of vapor so dense, it blocks nearly all light from penetrating deeper. Some researchers believe this could be the signature of a vast, superheated ocean, its surface perpetually boiling under the crushing weight of an atmosphere hundreds of times thicker than Earth's. Picture a pressure cooker the size of Neptune, where water exists in exotic, slushy forms, neither fully liquid nor entirely gas. But here's the twist: this planet's water might not even be water as we know it. Under such extreme pressures and temperatures, molecules break and reform into bizarre states. Scientists speculate that GJ1214b's depths could harbor hot ice, a crystalline form of water that stays solid even at scorching temperatures, or supercritical fluid, a chaotic phase where liquid and gas blur into one. And that's just the start. The planet's proximity to its star means it's tidally locked, with one side forever facing the heat while the other languishes in eternal twilight. This could create a perpetual hurricane of vaporized water racing from the day side to the night, where it might condense into eerie, high-pressure rain before cycling back again. What truly baffles astronomers isn't just the planet's composition, but how it formed in the first place. Conventional models suggest worlds like this shouldn't exist so close to their stars. Yet GJ1214b orbits 20 times nearer to its Sun than Mercury does to ours, challenging our understanding of planetary migration. Did it form farther out and spiral inward, gathering steam along the way, or was it born in some chaotic collision that left it swollen with water and shrouded in vapor? Every answer leads to new questions, making this steamy enigma a cornerstone in the search for habitable, or at least comprehensible worlds beyond our solar system. The deeper we probe, the more GJ1214b feels like a cosmic chimera, blurring the line between planet types. It's too dense to be a gas giant, too massive to be an ocean world, and too hot to fit any neat classification. And that's what makes it invaluable. By studying its impossible contradictions, we're not just unraveling the secrets of one oddball planet, we're rewriting the rules of what planets can be. In a universe teeming with surprises, GJ1214b stands as a steamy reminder that nature's imagination far surpasses our own. In 1572, a new star blazed so brightly in the constellation Cassiopeia that it outshone Venus, visible even in broad daylight for weeks. Astronomer Tycho Brahe, whose name would later grace this cosmic anomaly, described it as a miracle which has never before been seen since the beginning of the world. What he witnessed wasn't a newborn star, but the violent death throes of a white dwarf in a cataclysmic explosion we now call Tycho's supernova. Yet centuries later, astronomers made a chilling discovery: this star didn't die that day. Against all odds, it survived. Modern X-ray telescopes reveal the aftermath in stunning detail. The expanding debris field, a tangled web of shockwaves traveling at millions of miles per hour, paints a portrait of chaos. But buried within that wreckage lies something impossible: the stellar corpse that caused it, still intact. This zombie star defies the textbook fate of Type Ia supernova, where white dwarfs were thought to annihilate themselves completely in thermonuclear detonations. Tycho's remnant suggests a far messier truth. The leading theory: this white dwarf siphoned material from a companion star until it reached critical mass, triggering a runaway nuclear explosion. But instead of vanishing, it endured a partial detonation like a bomb that fizzled instead of fully exploding. Kepler's meticulous records of the event's fading glow now serve as critical clues, helping astronomers reconstruct the blast's power. By comparing 16th century brightness measurements with the remnant's current state, they've calculated how much energy the dwarf actually expelled, and it's less than expected. What saved it? One tantalizing possibility involves an asymmetric explosion, where the blast front ripped outward unevenly, leaving part of the dwarf's core unscathed. Chandra X-ray Observatory's images show telltale shadows in the debris, hinting at dense surviving fragments. Another twist: the companion star might still be there too, orbiting its undead partner in cosmic silence. If found, it would solve a centuries-old murder mystery, confirming the white dwarf's theft of stellar material led to its near-death experience. For astronomers, Tycho's zombie star is a goldmine of contradictions. Its existence challenges our understanding of stellar life cycles, proving some stars can cheat death in ways we never imagined. Every time we point telescopes at its glowing wreckage, we're not just studying an ancient explosion, we're witnessing a cosmic phoenix that refused to burn out. Imagine the entire universe as a vast river, with galaxies drifting together like leaves caught in an invisible current. Now imagine that current is flowing towards something we can't see, something beyond the edges of the known cosmos. This isn't science fiction, it's the dark flow, one of the most puzzling discoveries in modern astronomy. Clusters of galaxies, separated by billions of light years, all moving in the same direction at speeds exceeding 2 million miles per hour. And the reason, nobody knows for sure, but the answer might rewrite our understanding of reality itself. The dark flow was first detected in 2008, when astronomers studying the cosmic microwave background, the faint afterglow of the Big Bang, noticed something bizarre. The microwave patterns weren't perfectly uniform, as expected. Instead, they showed subtle ripples, as if something massive beyond our observable universe was tugging on everything within it. Further observations of hundreds of galaxy clusters confirmed the anomaly. These colossal structures, each containing thousands of galaxies, weren't just expanding with the universe. They were being pulled en masse toward a single point in space near the constellations Centaurus and Vela, a direction cosmologists now call the flow axis. What could possibly exert such gravitational influence? The leading explanation is terrifying in its implications. Our universe might be bumping up against another. In multiverse theories, other bubble universes could exist beyond the boundaries of our own, separated by membranes of higher dimensional space. If one of those bubbles lurked just outside our cosmic horizon, its gravity, though we can't see it, might be yanking on our galaxy clusters like a magnet. It's like standing in a pitch-black room, feeling a draft from a door you didn't know existed, but there's a catch. The dark flow contradicts one of cosmology's bedrock principles, the cosmological principle, which states that the universe should look roughly the same in all directions on large scales. If galaxies are streaming toward some unseen attractor that symmetry shatters, skeptics argue the observations could stem from measurement errors or local effects, though multiple studies have reinforced the finding. Others propose simpler alternatives, perhaps a supercluster of matter, trillions of times more massive than anything we've mapped, lies just beyond our observational limits. Then there's the truly radical idea: what if the dark flow isn't caused by matter at all? Some theorists speculate it could be evidence of quantum entanglement on cosmic scales, where distant parts of the universe remain mysteriously linked. Or maybe spacetime itself is subtly warped by processes we haven't yet imagined. Whatever the truth, this mystery forces us to confront a humbling possibility. The universe we see, all 14 billion light-years of it, might just be a speck in a far grander, stranger structure we're only beginning to sense. The dark flow isn't just a curiosity. It's a potential window into the beyond. If future telescopes confirm it stems from another universe, it would be the first tangible evidence that our cosmos isn't alone. Until then, those galaxy clusters keep drifting toward the unknown, carrying with them the tantalizing secret of what, or where, lies past the edge of everything. At the North Pole of Saturn, where swirling storms and hurricanes rage across its golden atmosphere, something impossible sits nestled in the clouds, a perfect hexagon. This six-sided jet stream, large enough to swallow 4 Earths side by side, spins with mathematical precision, its razor-sharp angles defying everything we know about planetary weather. Discovered by the Voyager probes in the 1980s, and later immortalized by Cassini's stunning close-ups, this colossal geometric storm has left scientists scratching their heads for decades. Hurricanes on Earth twist into spirals, storms on Jupiter churn in chaotic ovals, but Saturn's hexagon is nature's most baffling polygon, a structure so precise it looks like it was etched by an unseen cosmic hand. The numbers alone are staggering. Each side of the hexagon stretches nearly 9,000 miles, with winds screaming at over 200 miles per hour, yet the shape itself remains eerily stable, unchanging since we first observed it over 40 years ago. Unlike Earth's polar vortices, which shift and wobble with the seasons, this atmospheric anomaly locks into place like a spinning top, its corners pinned to Saturn's rotation. Infrared imaging reveals the hexagon towers hundreds of miles above the surrounding clouds, a towering wall of gas plunging deep into the planet's interior. But how does something so orderly emerge from a gaseous world with no solid surface to anchor it? Physicists have run supercomputer simulations, trying to recreate the hexagon in digital atmospheres. Some suggest the pattern stems from deep-rooted jet streams colliding at specific latitudes, generating standing waves that sculpt the gas into geometric shapes. Others propose it's a manifestation of fluid dynamics, like the hexagonal cells seen in laboratory experiments where liquids swirl under precise conditions. But none fully explain why Saturn's hexagon persists with such unwavering symmetry. Even stranger, the planet's south pole hosts a more conventional circular vortex, making the northern hexagon even more of an outlier. Cassini's images added eerie layers to the mystery. During Saturn's long polar winter, the hexagon became a cauldron of swirling hazes, its boundaries sharp as ever. When sunlight finally returned, cameras captured the structure glowing in ultraviolet, its edges lined with towering fog banks and bizarre, smaller vortices dancing along its perimeter like moons around a planet. The hexagon even changes color over time, shifting from blue-gold to ochre, hinting at chemical reactions we don't yet understand. What makes this phenomenon truly humbling is its defiance of categorization. It's not just a storm, it's a self-sustaining atmospheric machine, a celestial fingerprint of forces we've never witnessed elsewhere in the solar system. Could similar shapes lurk in the atmospheres of exoplanets? Are we missing some fundamental law of fluid motion that only gas giants can reveal? Saturn's hexagon refuses to answer, spinning silently in the dark, a riddle wrapped in golden clouds. Every time we think we've grasped its secrets, it reminds us that even the most familiar planets guard mysteries stranger than fiction. Most black holes announce their presence with violence, devouring stars, spewing radiation, or anchoring entire galaxies with their gravity. But not this one, drifting silently through the Milky Way, untethered from any star or system. A rogue black hole is carving its own path through the cosmos. Unlike its stationary counterparts, this lone wanderer doesn't blaze with the light of shredded matter or lurk at the center of a swirling disk. It's invisible, detectable only by the way it warps the fabric of space itself, a ghost in the galactic night. The first hint of its existence came from an eerie distortion in the night sky. As the rogue black hole passed between Earth and a distant star, its immense gravity bent the starlight, magnifying and twisting it like a cosmic funhouse mirror. This phenomenon, called gravitational lensing, created a fleeting spike in the star's brightness, a telltale signature of something massive, yet unseen. For the first time, astronomers glimpsed a black hole untethered from any stellar corpse or accretion disk, a solitary predator roaming the galaxy. If this phantom passed through our solar system, the consequences would be catastrophic. Even at a distance of a few light years, its gravitational pull could yank comets from the Oort cloud, sending icy projectiles hurtling toward the inner planets. Come too close and its tidal forces would shred worlds apart, stretching entire planets into spaghetti like strands before swallowing them whole. Unlike a supermassive black hole, which anchors galaxies with predictable orbits, this rogue is unpredictable, a cosmic wrecking ball with no fixed path. Yet for all its destructive potential, this wanderer is also a scientific treasure. Studying its motion could reveal secrets about how black holes form and what happens when they're ejected from their birthplaces, perhaps flung into the void by the recoil of a violent merger or the explosive death of a star. Some theories even suggest the Milky Way could harbor millions of these nomads, drifting unseen between the stars. The rogue black hole forces us to confront a humbling truth: the universe is filled with invisible dangers, lurking just beyond our perception. While the odds of a direct encounter are vanishingly small, its existence reminds us that space is anything but empty. It's a wilderness where ancient giants roam silent, unstoppable, and utterly indifferent to the worlds in their path. The universe isn't just a scattering of galaxies, it's a masterpiece of invisible architecture, woven together by colossal threads of gas and dark matter stretching billions of light years. These are the cosmic filaments, the hidden scaffolding of reality, where galaxies don't drift randomly but align like pearls on a string. Picture them as rivers of hydrogen gas, glowing faintly in the void, each one a highway guiding matter into the densest knots of the cosmic web where galaxy clusters form like glittering cities at the intersections. What makes these filaments so astonishing is how they trace the universe's skeleton. Most of their mass isn't even gas, it's dark matter, the mysterious substance that outweighs visible matter 5-to-1. Like invisible magnets, dark matter's gravity pulls gas into these sprawling tendrils, creating channels where galaxies are born. Simulations show that without this filamentary framework, the universe would be a formless sea of isolated stars. Instead, it's a dynamic network, constantly funneling fuel to galactic construction sites. But spotting these filaments isn't easy. Their hydrogen gas is so diffuse, it emits only a whisper of ultraviolet light. Astronomers had to invent new ways to see them, like using quasars as cosmic flashlights. When light from these ultra-bright galactic cores passes through filaments, the gas absorbs specific wavelengths, leaving fingerprint shadows in the quasar's spectrum. It's like holding a stained glass window up to the sun and mapping the colors that shine through. The sheer scale of these structures defies intuition. The Sloan Great Wall, one of the largest known filaments, spans over 1 billion light-years, a tendril so vast, it challenges theories about how quickly matter could clump together after the Big Bang. Other filaments like the one connecting the Pisces-Cetus supercluster twist and knot across the void, their shapes sculpted by ancient gravitational tides. And here's the eerie part, we're inside one too. The Milky Way resides in the outskirts of the Laniakea supercluster, a filament-fed metropolis of 100,000 galaxies. What's even wilder, these filaments aren't static, they hum with motion, channeling galaxies toward clusters in slow-motion rivers. Some galaxies, caught in the flow, move at over 800 miles per second, a phenomenon called dark flow, possibly driven by the pull of filaments we can't yet see. It's a reminder that even the emptiest corners of space are seething with invisible currents, guiding the universe's growth like unseen hands. The cosmic web isn't just a map of where matter is, it's a record of how the universe evolved. By studying filaments, we're deciphering gravity's blueprint, uncovering how dark matter shaped everything from the tiniest galaxy to the largest superclusters. And perhaps most thrilling, this web is still being spun. Even now, new filaments are stretching into the void, weaving the next chapter of cosmic history, one thread at a time. The Moon has no global magnetic field today, no protective shield like Earth's to deflect solar winds or guide compass needles. Yet when Apollo astronauts brought back lunar rocks in the late 1960s and early 70s, scientists made a baffling discovery. Some of those ancient samples were magnetized, as if frozen in time under the influence of a powerful magnetic field. How could this be? A world that's been geologically dead for billions of years shouldn't have the means to generate such forces. This lunar magnetism riddle has sparked decades of debate, with theories ranging from a long-lost core dynamo to cataclysmic impacts that briefly turned the Moon into a temporary magnet. One leading explanation hinges on the Moon's fiery youth. Early in its history, the lunar core might have churned with molten metal, creating a dynamo effect similar to Earth's, as spinning, conductive fluid generating a magnetic field. Computer models suggest this dynamo could have lasted for hundreds of millions of years, powered by the heat of the Moon's formation or tidal forces from a much closer Earth. But as the core cooled and solidified, the field would have faded, leaving only magnetized rocks as cryptic relics. Supporting this, some Apollo samples show magnetic signatures aligning with the Moon's ancient orientation, as if they recorded a consistent global field before it vanished. Then there's the impact hypothesis. The Moon's surface is a graveyard of colossal collisions, and some scientists argue these apocalyptic crashes could have generated fleeting magnetic fields. When a massive asteroid strikes, the explosion vaporizes rock, creating a superheated plasma. Charged particles swirling in this chaos, combined with the shockwaves rippling through the lunar crust, might briefly mimic a dynamo's effects. Imagine a lightning strike magnetizing a metal rod, but scaled up to planetary proportions. This could explain why magnetism seems patchy, concentrated near gigantic basins like Mare Imbrium, where impacts reshape the Moon's face. But the plot thickens. Recent lunar orbiter data reveals another twist. Certain surface regions produce localized magnetic anomalies, deflecting solar wind in miniature versions of Earth's magnetosphere. These magnetic bubbles don't match the ancient rock records, suggesting multiple mechanisms might be at play. Some researchers propose that slow-moving metallic asteroids could have left magnetic fingerprints as they plowed into the Moon, while others wonder if the Sun's magnetic field, imprinted during solar storms, might have selectively magnetized certain minerals. The implications stretch far beyond lunar geology. If the Moon once had a dynamo, it challenges our understanding of how small rocky bodies lose their heat. If impacts can forge temporary magnetic fields, it reshapes how we interpret magnetism on airless worlds across the solar system. Every new lunar mission, from China's Chang probes to future Artemis landings, brings fresh clues, peeling back layers of this enigma. The Moon's magnetic whispers are more than a curiosity. They're a window into the hidden forces that shape not just our closest neighbor, but every rocky world spinning in the dark. Rising from the heart of the Milky Way like twin ghosts stretching halfway across the visible sky, the Fermi bubbles are among the most colossal structures in our galaxy, yet you can't see them with the naked eye. Discovered in 2010 by NASA Fermi Gamma Ray Space Telescope, these towering lobes of ultra-hot gas and radiation extend 25,000 light-years above and below the galactic plane, pumping out gamma rays with energies that dwarf anything our sun could produce. Picture two vast balloons, each large enough to swallow 1,000 solar systems side by side, glowing faintly in high-energy light, but the real shock isn't their size, it's what they reveal about the Milky Way's violent past. At the base of these bubbles sits Sagittarius, a star, our galaxy's supermassive black hole. Normally quiet compared to its active cousins in other galaxies, this 4 million solar mass behemoth might have woken up in a cataclysmic feeding frenzy roughly 2.5 million years ago. As it devoured clouds of gas or entire stars, it would have belched out jets of charged particles and radiation, inflating the bubbles like cosmic bellows. The timing lines up eerily with geological evidence on Earth. Traces of radioactive isotopes in Antarctic ice cores suggest our planet was bathed in a surge of gamma rays around the same period. It's a chilling thought. While early humans were mastering fire, the center of our galaxy might have erupted with enough energy to sterilize nearby solar systems. But there's another, even wilder possibility. Some astronomers argue these bubbles aren't the aftermath of a single event, but the cumulative effect of countless stars being torn apart over eons. When a star wanders too close to the black hole, tidal forces stretch it into a glowing spaghetti strand, a phenomenon called a tidal disruption event. Each of these stellar deaths releases a burst of energy, and over millions of years, they could have stacked up like layers of an onion, slowly building the Fermi bubble's immense structure. Supporting this, the bubble's edges are remarkably sharp, as if sculpted by repeated shock waves from multiple explosions rather than one single outburst. What makes these gamma-ray ghosts so fascinating isn't just their origin, it's how they're reshaping our understanding of galactic ecosystems. The bubbles act like a pressure cooker, trapping high-energy particles that might otherwise escape into intergalactic space. Some researchers suspect they could be the source of mysterious cosmic rays that bombard Earth, particles accelerated to near-light speeds within these turbulent magnetic fields. Others have spotted faint X-ray counterparts to the bubbles, nicknamed the Irisida bubbles, suggesting this structure is even more complex than we first thought. The most humbling realization: if our solar system orbited closer to the galactic center, we'd be sitting inside one of these seething cauldrons of radiation, bathed in enough gamma rays to strip away atmospheres and fry DNA. Instead, we're distant witnesses to the Milky Way's hidden violence, catching only whispers of events that unfolded long before cities or telescopes existed. The Fermi bubbles are a reminder our galaxy isn't some serene island of stars. It's a living, breathing entity, capable of eruptions that dwarf anything in human history. And somewhere in their swirling depths lies the answer to one of astronomy's biggest questions: just how often does the sleeping giant at the heart of our galaxy wake up? Of all the cosmic rule breakers in the early universe, few defy logic as brazenly as ULA's J1342 plus 928. This quasar, blazing just 108 million years after the Big Bang, shouldn't exist, yet there it glows, a cosmic paradox written in light. At its heart lies a supermassive black hole weighing in at 800 million times the mass of our Sun, a monster so colossal it challenges our fundamental understanding of how these gravitational giants grow. According to conventional models, black holes this size need billions of years to form, feasting slowly on gas and merging with smaller siblings, but this one appeared when the universe was barely 5% of its current age, as if it skipped the line in cosmic evolution. What makes this quasar so baffling isn't just its size, it's the sheer speed of its ascent. To reach such staggering mass so quickly, its black hole would have needed to gorge on matter at the theoretical maximum rate for its entire existence, violating what we know about feeding limits. Imagine trying to fill an Olympic-sized swimming pool with a garden hose, only to discover someone did it in seconds. Astronomers call this the Eddington limit problem, the physics that says black holes can't consume material faster than the radiation pressure from their own meals allows. Yet ULA's J1342 plus R928 somehow bypassed those rules, growing at a pace that leaves theorists scrambling for explanations. One radical possibility: this black hole didn't grow gradually at all, it was born big. In the universe's chaotic infancy, direct collapse black holes might have formed from the instantaneous collapse of gargantuan gas clouds, skipping the star stage entirely. Picture a primordial nebula, dense and turbulent, collapsing directly into a black hole with tens of thousands of solar masses, right out of the gate, a cosmic shortcut to supermassive status. Others speculate that early black holes merged with freakish efficiency, their growth turbocharged by environmental conditions we've never observed in the modern cosmos. The early universe was a denser, hotter place, packed with gas-rich galaxies ripe for the taking. Perhaps black holes back then feasted like kings at a banquet, while their modern counterparts scrape by on cosmic crumbs. Then there's the quasar's light, another puzzle. Its spectrum reveals it was already surrounded by heavy elements like carbon and iron when the universe was barely out of diapers. These metals only form in the hearts of stars and are scattered by supernova, meaning stars had to die, and enrich the cosmos at breakneck speed for this quasar's environment to exist. It's like finding a fully furnished skyscraper in the middle of a freshly cleared construction site. Every time we discover such an impossible quasar, it chips away at our cosmic timeline, forcing us to reconsider how quickly structures emerged from the primordial dark. ULA's J1342 plus R928 isn't just an outlier, it's a siren, calling us to rewrite the story of the universe's wild youth. If black holes could grow this fast, what else did we get wrong about the dawn of time? The Whirlpool Galaxy is a cosmic pinwheel, its graceful spiral arms spinning through space in a mesmerizing dance of stars and gas. But look closer, and you'll spot the troublemaker responsible for its stunning chaos: a smaller, misshapen galaxy called M51b, clinging to the Whirlpool's outer arm like a child tugging at a parent's sleeve. This cosmic duo, locked in a gravitational tango 23 million light-years away, is rewriting the rules of galactic interaction, proving that even the most beautiful structures in the universe are born from violence. Hubble's razor-sharp images reveal the drama in vivid detail. As M51b swings past its larger companion, its gravity yanks vast streams of gas and dust from the Whirlpool's arms, stretching them into jagged arcs that glow with newborn stars. These tidal tales, some spanning tens of thousands of light-years, are cosmic nurseries where compressed gas collapses into fiery stellar infants. The smaller galaxy isn't just distorting the Whirlpool, it's forcing it to create. Without this gravitational bully, the Whirlpool's iconic spirals might have remained smooth and symmetrical, devoid of the brilliant blue star clusters that now stud its disrupted arms. But here's the twist: M51b is paying a price for its interference. The Whirlpool's far greater mass is slowly shredding the smaller galaxy, stripping away its stars and gas in a process called tidal disruption. Infrared observations show M51b's core blazing with star formation, a last gasp of activity as its remaining gas, compressed by the encounter, ignites into furious stellar birth. Over billions of years, this relentless tug-of-war may leave the smaller galaxy a ghostly shell, its stars scattered into the Whirlpool's halo like cosmic confetti. What makes this pair so fascinating isn't just their destruction, but their creativity. Galactic collisions were once thought to be rare catastrophes, but we now know they're the universe's favorite sculptor. The Whirlpool and its companion are a preview of our own Milky Way's fate. when it collides with Andromeda in 4 billion years, a slow-motion crash that will trigger a firestorm of star birth, reshape both galaxies beyond recognition, and leave behind a single, scrambled hybrid. Yet M51b offers another lesson: size doesn't dictate influence. This dwarf galaxy, a fraction of the whirlpool's mass, has altered its giant neighbor's structure more profoundly than any internal force could. It's a reminder that even the smallest players can leave the grandest marks on the cosmos. As we watch their dance unfold across millions of years, we're witnessing the engine of galactic evolution, one gravitational nudge, one stellar explosion, one stolen stream of gas at a time. Zeta Ophiuchi isn't just another bright point in the night sky, it's a cosmic fugitive, hurtling through space at 54,000 miles per hour, leaving a trail of chaos in its wake. This massive blue star, 20 times heavier than our Sun, races against the backdrop of interstellar dust like a bullet tearing through smoke, its path marked by a colossal bow shock that glows in infrared light. But here's the mystery: stars this size don't just pack up and sprint across the galaxy without a reason. The leading theory, Zeta Ophiuchi was once part of a binary system, until its companion star went supernova in a catastrophic explosion, kicking it into space like a pebble from a slingshot. The evidence lies in the star's wake. As Zeta Ophiuchi plows through dense clouds of gas and dust, its immense stellar wind, a stream of charged particles blowing outward at nearly 1,000,000 miles per hour, collides with the interstellar medium. The result is a dramatic shockwave, visible as a glowing arc ahead of the star, where material compresses and heats up. This bow shock spans over 4 light years, a vast ripple in the cosmic pond that reveals the sheer force of the star's motion. Yet despite its speed, Zeta Ophiuchi isn't leaving quietly. The turbulent interaction lights up surrounding dust in vibrant hues, a celestial fingerprint of its reckless journey. But the supernova kick theory isn't the only possibility. Some researchers suggest the star might have been ejected by gravitational interactions in a dense star cluster, slingshotting past other massive bodies until it broke free. Computer simulations show that in crowded stellar nurseries, close encounters between stars can fling one member outward at extreme velocities. If true, Zeta Ophiuchi's story isn't just about destruction, it's a tale of celestial billiards, where one wrong move sent it careening into the void. What makes this runaway so fascinating isn't just its speed, it's the temporary mark it's leaving on the galaxy. The shockwaves it generates are compressing nearby gas, potentially triggering new star formation in its path. Imagine a cosmic snowplow, carving a wake where future suns might one day ignite, and here's the bittersweet twist: Zeta Ophiuchi itself is doomed. Stars this massive live fast and die young, destined to explode as supernova within a few million years. When it does, its own explosion might send another star fleeing, continuing the cycle of chaos and rebirth. For astronomers, Zeta Ophiuchi is a rare glimpse into the volatile lives of massive stars. Most runaways are too distant or faint to study in detail, but this one is close enough, just 460 light-years away, to reveal the intricate physics of its escape. Every observation peels back another layer, showing how the universe's most powerful forces can turn a star into a wanderer, rewriting its destiny in a single, violent moment. In the grand cosmic dance, Zeta Ophiuchi is the rebel that broke formation, and its story is far from over. Hidden in the afterglow of the Big Bang, the cosmic microwave background that blankets the universe, there's a mysterious cold patch so large and unexpected, it shouldn't exist. Stretching nearly 2 billion light-years across the constellation Eridanus, the cold spot is a cosmic bruise, a region significantly chillier than its surroundings with no obvious explanation. Some astronomers call it a supervoid, a vast, empty bubble in the cosmic web where the absence of galaxies and matter allows space itself to cool as light loses energy crossing it. Others whisper about collisions with parallel universes or flaws in our understanding of physics. One thing's certain: this anomaly refuses to fit neatly into our models of how the universe works. At first glance, the supervoid theory seems plausible. If the cold spot were just an enormous cosmic desert, a place where gravity pulled galaxies away, leaving behind a relative vacuum, the expansion of space within it would stretch photons from the cosmic microwave background, shifting them to longer, cooler wavelengths. But there's a problem. Measurements show the void isn't nearly empty enough to account for the temperature drop. Even with fewer galaxies, the observed cooling is too extreme, as if something drained not just matter but energy from this region of space. It's like opening your freezer to find one corner inexplicably colder than the rest, with no insulation or coolant to explain it. Then there's the multiverse angle. Some theorists propose the cold spot could be an imprint from a collision with another bubble universe during cosmic inflation, the rapid expansion of spacetime just after the Big Bang. In this scenario, our universe might have brushed against another, their energies briefly interacting like soap bubbles touching, leaving behind a thermal fingerprint in the form of this frigid anomaly. While tantalizing, there's no direct evidence to support this. Skeptics argue it's more likely an observational error or statistical fluke, though multiple independent studies have confirmed the cold spot's existence. What makes this enigma so compelling is its sheer scale. If real, it challenges the cosmological principle, the idea that, on large scales, the universe should look roughly the same in all directions. A structure this big and this cold throws that assumption into question. Could there be other anomalies lurking in the cosmic microwave background, remnants of processes we don't yet understand? Or is the cold spot a cosmic illusion, a trick of overlapping smaller voids that only appears as one colossal structure from our vantage point? Every new observation deepens the mystery. Some recent studies suggest the cold spot might not be entirely empty. Instead, it could host a sparse network of galaxy clusters, arranged in a way that magnifies its chilling effect. Others propose exotic physics, like dark energy interacting differently in this region, or quantum fluctuations frozen into the early universe. Whatever the truth, the cold spot remains one of cosmology's most stubborn puzzles, a reminder that even our most precise maps of the cosmos still hold uncharted territories. Until we can peer deeper or devise new ways to test these theories, it stands as a silent question mark written in the coldest ink of the universe. In the constellation Hercules, a celestial enigma glows with an eerie blue light, the Blue Ring Nebula, a cosmic crime scene where two stars may have become one. Unlike the colorful, symmetrical nebulae we're used to seeing, this one sports a bizarre ultraviolet ring, a ghostly halo that baffled scientists for nearly 2 decades after its discovery in 2004. Recent spectroscopic analysis has peeled back layers of the mystery, revealing what might be the aftermath of a stellar merger, a violent embrace that left behind a single, reshaped star cloaked in debris. At the heart of the nebula lies TUE 2597-160-1, a star whose light carries strange chemical fingerprints. Its spectrum shows excess helium and molecular hydrogen, along with shock waves rippling through surrounding gas, all telltale signs of a catastrophic collision. The leading theory goes like this: millions of years ago, two stars orbited each other in a tight dance. As one aged into a red giant, swelling to engulf its partner, the smaller star spiraled inward, triggering a merger that ejected massive amounts of material into space. That explosive farewell created the nebula's expanding shell, now illuminated by the ultraviolet glare of the surviving star's hot core. But the real puzzle is that blue ring. It's not actually blue to the naked eye. The hue comes from false color imaging that highlights intense ultraviolet emission from hydrogen molecules. These molecules, excited by the central star's radiation, glow in a way that forms a perfect circle. But here's the twist: the ring isn't a flat structure. It's a cone-shaped debris field viewed nearly face-on, with shock fronts where ejected material slams into interstellar gas. The symmetry is so precise, it looks engineered, as if the universe itself drafted geometric blueprints for this stellar aftermath. What makes this discovery groundbreaking isn't just the merger scenario, it's the rarity of catching one in this stage. Most stellar collisions are either too messy or too faded to study clearly, but the Blue Ring Nebula offers a snapshot of the brief phase when ejected material hasn't yet dispersed into the void. By analyzing its light, astronomers have reconstructed the timeline. The merger likely occurred a few thousand years ago, and the ejected shell is racing outward at about 50 miles per second. That's slow enough to dissect in detail, yet fast enough to watch changes unfold over human timescales, yet some questions still linger. Why does the central star rotate so slowly, unlike most merger survivors? Could magnetic fields have braked its spin, or was the collision oddly gentle despite its violence? And where are the expected heavier elements, usually forged in such cosmic smash-ups? Each answer leads to new mysteries, proving that even in death, stars refuse to follow the script. The Blue Ring Nebula isn't just a relic, it's a living laboratory, rewriting our understanding of how stars cheat death, reshape their destinies, and leave behind the universe's most hauntingly beautiful graffiti. Drifting through the cosmic deep, 300 million light-years from Earth, the Tadpole Galaxy stretches across space like a celestial ink blot, a spiral galaxy with a tail so long, it could wrap around the Milky Way twice. This isn't some serene island of stars, it's a survivor of one of the universe's most violent ballets. What we're seeing is the aftermath of a high-speed collision, a gravitational sideswipe so powerful it ripped a trail of stars, gas, and dust hundreds of thousands of light-years into the void. The culprit, a smaller intruder galaxy that barreled through the tadpole's disk, its gravity acting like a cosmic plow, churning the spiral's structure into chaos. Hubble's images reveal the drama in stunning detail. The tadpole's main body still clings to its spiral shape, though warped and misshapen, while its tail, a glittering stream of blue star clusters and pink nebulae, arches into space like a comet's trail. Those blue knots aren't just debris, they're stellar nurseries, ignited by the collision's shockwaves compressing gas into fiery new suns. It's a paradox of destruction and creation. The same event that tore the galaxy apart also seeded its future. And that tail isn't static. Over millions of years it will stretch farther, its outermost stars drifting away forever, while the densest clumps may coalesce into dwarf galaxies, satellites born from violence. What makes the tadpole so fascinating isn't just its appearance, but what it teaches us about galactic resilience. Most galaxies bear scars from past encounters, but few showcase the process so vividly. By studying its tail's chemistry, astronomers have found metals forged in earlier generations of stars, proof that the tadpole was already mature when the collision happened. Its spiral arms, though distorted, still rotate, suggesting the galaxy's core survived the encounter intact. Even more remarkable, the intruder galaxy likely got the worse end of the deal. Simulations show it was probably shredded by the encounter, its stars scattered into the tadpole's halo, or flung into intergalactic space. This cosmic tug-of-war also offers a preview of our own galaxy's fate. In 4 billion years, when the Milky Way collides with Andromeda, we might witness a similar spectacle, tidal tales of stars arcing into the darkness, new suns igniting in the chaos. But the tadpole's story holds a quieter lesson too. Given enough time, even the most dramatic wounds heal. The tail will fade, the spiral arms will settle, and the galaxy will resume its stately rotation, a testament to the universe's knack for turning chaos into something breathtaking. For now it drifts as a frozen moment in a billion-year dance, reminding us that beauty in space often comes from catastrophe. Galaxies aren't supposed to defy the rules, they're bound by gravity, sculpted by dark matter, their very existence dependent on the invisible scaffolding of the cosmos. But in UC 1052 DF2 doesn't just bend the rules, it snaps them in half. This ghostly galaxy, floating 65 million light-years away in the constellation Cetus, is missing something fundamental: dark matter. The stuff that makes up 85% of the universe's mass, the glue that holds galaxies together, the hidden hand guiding their birth and evolution somehow, this cosmic rebel exists without it. At first glance, and you see 1052 DF2 looks like any other ultra-diffuse galaxy, a wispy, translucent smudge of stars so spread out you could fly through it for thousands of light-years and barely notice. But when astronomers measured its motion in 2018, they stumbled into pure disbelief. The stars within it moved far slower than expected, their velocities suggesting the galaxy weighed almost nothing beyond its visible stars and gas. No dark matter halo, no hidden mass, just starlight and silence. This shouldn't be possible. Every known galaxy, from spirals like the Milky Way to dwarf satellites, is cradled in a cocoon of dark matter. Without it, early gas clouds wouldn't have clumped together to form stars in the first place. Dark matter's gravity is the cosmic puppeteer. It dictates where galaxies form, how they spin, even how they collide. So how did NUC 1052 DF2 escape the universe's most fundamental architect? One radical theory suggests it might be a tidal dwarf, a galaxy born from debris ejected during a violent collision between larger galaxies. In this scenario, the expelled gas and stars, already stripped of dark matter from their parent galaxies, could have coalesced into this eerie anomaly. Another idea posits that dark matter was somehow scraped away by a close encounter with a massive neighbor, though no such culprit has been found, the most unsettling possibility. Dark matter isn't as universal as we thought. Could there be rare pockets of the cosmos where the rules are different, but the plot thickens? Further studies revealed NGC 1052 DF2 isn't alone. Its neighbor NGC 1052 DF4 also shows suspiciously low dark matter levels, hinting at something strange happening in this galactic neighborhood. Some astronomers argue these oddballs might actually prove dark matter exists because without it, their fragile structures should have unraveled eons ago. The debate rages on, with every new observation adding twists. Recently, a team suggested the galaxy might be closer than we thought, which would revise its mass calculations, but even then, the dark matter deficit remains stark. What makes this ghost galaxy so compelling isn't just the mystery, it's the defiance. If dark matter is the universe's invisible skeleton, NGC 1052 DF2 is a living body without bones, challenging us to rethink how galaxies live and die. Whether it's a cosmic fluke or a sign of deeper physics we've yet to grasp, one thing's certain: the universe loves proving that even its most ironclad laws have exceptions. And in those exceptions, we often find the keys to its greatest secrets. Moonlight shouldn't exist 4,000 light-years from Earth, yet astronomers might have found it. Orbiting the gas giant Kepler 1625b, a shadow flickers in the data, hinting at something unprecedented. Kepler 1625bi, the first potential exomoon ever detected. If confirmed, this isn't some cratered rock like our moon. This is a Neptune-sized behemoth, a moon so colossal it dwarfs every satellite in our solar system and blurs the line between planet and moon. The evidence comes from subtle dips in starlight. When Kepler 1625b transits its sun, blocking a fraction of the star's glow, Hubble's precision instruments caught something odd: a secondary dimming, a faint echo of the main event. This tiny blip, lasting just a few hours, suggests something massive trailing the planet, its gravity bending light in tandem. But here's the catch: exomoons are notoriously hard to spot. Their signals drown in the noise of planetary transits, like trying to hear a whisper in a hurricane. That's why this candidate, observed in 2017, sent shockwaves through astronomy. The data fit the profile of a moon roughly 4% the mass of its host planet, a ratio that would make our moon look like a pebble beside Earth. Yet skepticism lingers. The universe loves to mimic phenomena, and alternative explanations abound. Could the signal be a second planet in a resonant orbit? Or perhaps a glitch in Hubble's instruments, amplified by wishful thinking? The moon's sheer size fuels doubt. In our solar system, moons are tiny compared to their parents. Ganymede, the largest, is just 2% Jupiter's mass. A Neptune-sized satellite defies convention, suggesting either a captured rogue planet or a violent collision that launched a moon into orbit. The stakes couldn't be higher. Confirming Kepler's 1625b, I would prove moons exist in other star systems, expanding the playing field for habitability. Imagine a gas giant's moon, warmed by tidal forces, hosting oceans under a thick atmosphere. But until more observations rule out false positives, this cosmic oddity remains a tantalizing maybe. Future telescopes like the James Webb might finally settle the debate, peering into the glare of distant stars to hunt for shadows that shouldn't be there. For now, it's a celestial tease, a glimpse of a universe where moons might rival planets, and the familiar rules of our solar system crumble. We measure our lives in Earth years, 365 days of seasons, birthdays, and routines. But zoom out to the scale of our galaxy, and time stretches into something almost incomprehensible. The Sun, like every star in the Milky Way, is on its own epic journey, orbiting the galactic center once every 230 million Earth years. Astronomers call this a galactic year, a single revolution so vast it makes human history look like the blink of an eye. Consider this: the last time our solar system was in its current position, dinosaurs ruled the Earth. The Jurassic period was in full swing, with towering sauropods grazing on fern-covered plains. In the 230 million years since, our Sun has completed just one full lap around the galaxy. The entire reign of the dinosaurs, from their rise to their asteroid-driven fall, played out in less than half a galactic year. Even more staggering, modern humans have existed for roughly 1/1000th of a single orbit. Our entire species, with all its civilizations and discoveries, hasn't even made a dent in the cosmic calendar. But here's where it gets mind-bending. While the Sun's path seems stately from afar, it's anything but slow. Our solar system hurtles through the Milky Way at 515,000 miles per hour, fast enough to cross the distance from Earth to the Moon in under half an hour. Yet because the galaxy is so unfathomably large, even at this breakneck speed, a full circuit takes ages. Picture a car racing around a track the size of a continent. You'd be moving fast, but the sheer scale makes each lap feel eternal. The galactic year also reshapes how we think of cosmic events: massive asteroid impacts, supervolcano eruptions, even the formation of mountain ranges. All these geological upheavals are mere footnotes in a single orbit. And the galaxy itself is evolving faster than our Sun can circle it. Stars are born, die, and drift, spiral arms twist and merge. By the time we complete another lap, the Milky Way will have collided with Andromeda, reshaping our celestial neighborhood beyond recognition. What does this mean for us? It's a humbling reminder that the universe operates on timelines we can barely grasp. The rise and fall of species, the shifting of continents, even the lifespan of stars, they're all just ripples in a current flowing on scales that defy human intuition. The galactic year isn't just a measure of time, it's a lens through which we see how small, how fleeting, and how incredibly recent our story really is. Stars die once, or at least that's what we thought until IPTF-14 HLS came along. This cosmic rebel didn't just explode, it erupted, faded, and then exploded again like a celestial phoenix refusing to stay dead. Discovered in 2014 by the Intermediate Palomar Transient Factory, this so-called supernova initially seemed ordinary until astronomers checked historical plates and realized the same spot had flared brightly in 1954. Somehow this star had survived its own death throes not just once, but repeatedly over decades, rewriting every rule we had about stellar explosions. A typical supernova is a one-and-done affair. A massive star exhausts its fuel, collapses under its own gravity and detonates in a single, cataclysmic blast that scatters its guts across light years. The aftermath, a neutron star or black hole, and a fading glow of radioactive debris, IPTF-14 laughed in the face of convention. Instead of dimming steadily after its initial explosion, its brightness oscillated for nearly 2 years, surging and waning like a cosmic heartbeat. Even stranger, its spectra revealed slow-moving, hydrogen-rich ejecta, something usually seen in younger supernovae, not ones lingering for half a century. It was as if the star had layered explosions, each peeling back a shell of material like an interstellar onion. The leading explanation, the pulsational pair instability theory, sounds like something from astrophysical fan fiction. In this scenario, a star over 130 times the Sun's mass becomes so hot in its core that photons spontaneously convert into electron-positron pairs. This steals energy from the star's core, causing partial collapses that trigger multiple explosive eruptions before the final, fatal blast. Think of it as a stellar engine misfiring, belching out layers of itself in violent hiccups before the whole thing finally gives out. If confirmed, IPTF-14 would be the first real-world evidence of this ultra-rare phenomenon, a relic from the early universe when monster stars were more common. Yet even this theory doesn't explain everything. The energy released over IPTF-14's lifetime exceeds what pair instability models predict, and the star's location, in a relatively modern galaxy, clashes with expectations that such behemoths should only exist in primordial cosmic conditions. Some astronomers speculate a magnetar, a highly magnetized neutron star, might be powering the prolonged fireworks, while others wonder if we're seeing a black hole consuming a companion star in slow motion. Every new observation deepens the mystery, proving that when it comes to stellar deaths, the universe has a flair for the dramatic. What makes IPTF-14 so thrilling isn't just its defiance of physics textbooks, it's the reminder that even the most violent events in the cosmos can hide layers of nuance. Most supernovae are blink and you'll miss it spectacles, but this one unfolded like a multi-act tragedy, challenging astronomers to rethink what it means for a star to die. As telescopes continue monitoring its fading remnants, one thing's certain: somewhere in its turbulent past lies a clue to stellar behaviors we've barely begun to imagine. The night sky holds galaxies that dazzle with billions of stars, spirals like Andromeda, blazing with light, but Dragonfly 44 is the opposite, a shadowy enigma hovering in the constellation Coma Berenices. This dim, diffuse galaxy emits just 1% the light of the Milky Way, yet it weighs just as much. The reason? It's almost entirely made of dark matter, a cosmic ghost town where the invisible outweighs the visible 10,000 to 1. Discovered in 2015 by the Dragonfly Telephoto Array, a telescope built from repurposed camera lenses, this galaxy defies every expectation. At first glance, it resembles a smudge, its stars so sparse you could fly through it for light years without spotting one. But when astronomers measured its rotation, they got a shock. The few visible stars whirled at speeds that should have flung them into the void, unless something unseen was holding them together. That something, a staggering halo of dark matter, accounting for 99.99% of the galaxy's mass. This raises a cosmic chicken and egg riddle. Did Dragonfly 44 form because of dark matter, or did it lose its stars over time? One theory suggests it's a failed galaxy, a primordial clump of dark matter that never gathered enough gas to birth stars efficiently. Another posits it was stripped bare by gravitational interactions, its stars ripped away while its dark matter skeleton remained intact. Supporting this, Dragonfly 44 sits near the crowded Coma cluster, a region where galaxies often collide and cannibalize each other. Yet the mystery deepens. Ultra-diffuse galaxies like this shouldn't survive long in such a turbulent neighborhood. Their fragile structures ought to disintegrate. Dragonfly 44 Resilience hints that dark matter isn't just an anchor, it's a cosmic shield, distributing gravity in ways that stabilize delicate star systems against external chaos. The most haunting question isn't how Dragonfly 44 exists, but how many more lurk unseen. Current telescopes might only catch the brightest of these phantoms. If dark galaxies outnumber luminous ones, the universe's true architecture could be a web of shadows, with places like the Milky Way as rare exceptions in a dark matter-dominated cosmos. Dragonfly 44 isn't just an oddity, it's a key to the universe's hidden blueprint, written in ink we're only beginning to perceive. The cosmic microwave background, the faint glow from the birth of the universe, should be the ultimate equalizer, a perfectly uniform canvas of radiation stretching across the sky. But in 2005, astronomers spotted something unsettling. This primordial light isn't just random static, it shows eerie alignments along a single axis, nicknamed the axis of evil. This bizarre pattern suggests the universe might have a preferred direction, a cosmic north that defies our deepest assumptions about the Big Bang and the very fabric of space-time. At the heart of the controversy is the CMB's quadrupole and octupole moments, fancy terms for the way its temperature fluctuations are distributed. Instead of being scattered randomly like confetti, these fluctuations line up along a mysterious axis that slices through the constellations Leo and Aquarius. It's as if the universe rolled a cosmic die and it kept landing on the same number over and over, for a theory built on the principle that the cosmos has no special direction, no up or down on the grandest scales. This is more than inconvenient. It's potentially revolutionary. The implications are staggering. If the axis of evil is real, it could mean the universe isn't isotropic, that space itself has a grain, like cosmic wood, with properties that vary depending on which way you're facing. One radical explanation invokes pre-Big Bang physics, suggesting our universe might have inherited this alignment from an earlier epoch, like a fingerprint left by whatever came before inflation. Others propose wilder ideas. Could the universe be rotating? Or worse, are we seeing the gravitational imprint of a neighboring universe brushing against ours, leaving wrinkles in spacetime that never fully smoothed out? Skeptics argue it's all an illusion. The alignment could stem from local contamination, dust in our galaxy, quirks in our telescopes, or even the gravitational lensing effect of nearby galaxy clusters warping the CMB's light. But after nearly 2 decades of scrutiny, the axis of evil refuses to vanish. Planck satellite data, the gold standard for CMB measurements, still shows the anomaly, albeit slightly muted. It's as if the universe is whispering a secret we're not quite equipped to hear. What makes this cosmic oddity so electrifying isn't just the anomaly itself, it's the philosophical earthquake it triggers. The standard model of cosmology rests on the idea that the universe is fundamentally the same everywhere. If that's wrong, the foundations of modern physics might need a rewrite. The axis of evil isn't just a scientific curiosity, it's a dare, a challenge to look deeper, question harder, and admit that even our best theories might only be fragments of a truth far stranger than we've imagined. From rogue black holes drifting unseen through the cosmos to galaxies made almost entirely of dark matter, these 30 cosmic oddities prove one thing: the universe thrives on the unexpected. Every corner of space hides phenomena that defy logic, rewrite textbooks, and leave even the sharpest scientific minds in awe. Whether it's a star that refuses to die, a nebula shaped like a perfect rectangle, or a supermassive black hole that somehow existed at the dawn of time, each discovery peels back another layer of the universe's infinite creativity. Think about it, these aren't just quirks, they're clues. The hexagon storm on Saturn could teach us about fluid dynamics we've never imagined. The missing dark matter in NGC 1052 DF2 might hint at physics beyond our current models. Even the eerie silence of the Boötes void forces us to question how much of reality is just empty space. Every oddity on this list is a puzzle piece, waiting to slot into the grander picture of how everything from the tiniest atom to the largest supercluster fits together. And here's the best part, this is just the beginning. For every mystery we've uncovered, there are thousands more lurking in the data, hidden in telescope static, or drifting unseen in the void. The universe isn't just weirder than we imagine, it's weirder than we can imagine. So stay curious, keep staring up at the night sky and wondering what else is out there. If this cosmic roller coaster left you hungry for more, hit subscribe. We've got endless deep dives into space's greatest enigmas coming your way, and drop a comment below, which oddity blew your mind the most. The diamond planet, the zombie star, or something even stranger? Let's keep the conversation as limitless as the cosmos itself. Remember, the universe doesn't play by the rules, and that's what makes exploring it so thrilling.